In this video, we introduce a third counting rule. So the first two that we talked about were arrangements, and then arrangements with without repetition, or we could call those permutations. In this video, let's talk about combinations. Right? So the only difference between combinations and permutations is that the order of the arrangement no longer matters to us. Right? So we're selecting groups of things, perhaps committees, or just three numbers, or a group of three people, but we don't care what order those things are in. So here is the combinations rule, and I think if we do an example, I think this will make maybe more sense than going through the variables in the rule. But notice that there are three different ways to calculate a combination. The first way is to find this calculator key, and the only thing you would need to know is the total number of items that you're choosing from, and then how many things you're trying to choose. All right, so like if you have 10 people and you're picking a group of 3, then in your calculator you can do 10C3 and make that calculation. The second way to calculate combinations is by observing that there's a relationship between them and permutations, and that they are just the numbers of permutations or arrangements of something, and then we want to just divide to get rid of all of the different orders of something. Right? And then the third way to do this is the longest way, but it's handy if you don't have a calculator. You can use the combinations formula and do this by hand. So here's our example. Suppose that the 5 members of a city council decide that they need a 3-person committee to study the impact of a new shopping center. The council members are Ursula, Vern, Wendy, Yolanda, and Zeke, conveniently so that we can call them U, V, W, Y, and Z. How many 3-person committees can be formed from the 5 council members? All right, so our N is 5. We have 5 people to pick from, and the R is 3. That's the number of things that we're trying to choose. All right, so let's start by using permutations to try to answer this question. So how many options are there for the first person in the 3-person committee? Okay, there are 5. And then since we can't repeat a person, because then that would technically be a 2-person committee, not a 3-person committee, now we only have 4 people left for the second member, and then that leaves us with 3 people, and one of them will get picked to be the 3rd person on the committee. And then that will leave out 2 people that are not on the committee. All right, so if you multiply, that gives you 60 different options. But keep in mind, this does include some repeat options that are just in different orders. All right, so let's say we picked Ursula first, and then we picked Vern and then Wendy. Okay, now any of the 5 people could have been chosen first. So let's say that Wendy was picked first, right? And then maybe we would pick Vern next and then Ursula. Well, really notice that those are the same 3-person committee. We just picked them in a different order. But in this problem, we don't really care about the order that they were picked in. There aren't different roles on the committee. They all have an equal part. So really order makes no difference. Right? So that's why we want to treat this as a combination. All right, so now the question is, out of this list of all 60 different arrangements, how do we get rid of the overcounting that happened? Right? And that's really answering the question, how many ways are there once we've picked a particular 3-person committee like Ursula, Vern, Wendy, how many ways are there to arrange those people? And we've answered that question before too. It's really just a factorial, and we can list it out just to emphasize this. So we could have Ursula, Vern, Wendy, Ursula, Wendy, Vern, Vern, Ursula, Wendy, Vern, Wendy, Ursula, or Wendy, Ursula, Vern, Wendy, Vern, Ursula. Okay, so there are 6 different ways to arrange any particular 3-person committee. And if you don't feel like writing that all out, we could just multiply 3 times 2 times 1, or do 3 factorial. Okay, so we've overcounted everybody by 6. Right, so to find the correct number of combinations here, we just need to take the 60 and divide by the 6, and then we can see that there are 10 different combinations. And if you did your textbook reading before watching this video, then you can see that they did start by listing out all of the different combinations and possibilities for the committees. So this is a small enough group here that you could do the same and just list out the 10. Okay, so let's notice the connection with permutations here. All right, so this answer is 10. All right, so what we did first was calculate the permutations, and I did this by multiplying, but we could have also used the permutations rule. We could have done 5p3, 5 people, choose and arrange 3 of them. And then we would need to divide that by 3 factorial, or once we've got our group of 3, how many ways are there to arrange those 3 people? Okay, and that's where we're getting the 10. So if you want to make sure that this is the same, you can enter this in your calculator, try it out, and make sure you do get 10. All right, and then what would this look like if we write this all out by hand? All right, well, 5p3 is 5 factorial divided by 5 minus 3 factorial. So that's the part that helps us, that division helps us stop counting when we get to 3 and not continue on to 2 times 1. Okay. In addition to that, we also are dividing by 3 factorial, and the purpose of that division is to get rid of the different orders of the 3 people and just consider the number of distinct groups overall. So now going back to our formula in general, we can find the number of combinations by starting with arrangements and then just dividing to get rid of the order of each group that we picked, right? Or if you do this by hand, this first part of the formula is the permutation, okay? And the second part is to get rid of the different orders. Now, which of these you use, I think, is mostly based on your personal preference. For me, it comes down to how fast it is to do by hand versus do I want to use a calculator. So if this were something, anything where n is larger than, I don't know, I would say 10 or something like that, I probably would just use a calculator. But like if I had 26 letters of the alphabet and how many ways are there to pick 5 of them? Okay, well I know I'm at least going to have to do 5 multiplications and then some divisions, so I probably would use a calculator. But something like 10, choose 2, I would do that one by hand. All right, so if I looked at permutations or arrangements of 2 out of 10 things, well that's 10 times 9, 10 options for the first thing, 9 for the second. And then to make combinations and not permutations, I want to divide by how many times I've overcounted. All right, so each of my groups of 2 things was counted in 2 factorial different orders. Okay, so like if I picked A and B as my 2 things, then I counted 90 permutations because I counted A and B and B and A, okay, and C and D and C and so forth. All right, so dividing gets rid of the double counting. So for me, it's faster to just do 10 times 9 is 90, divided by 2 is 45, rather than dig out a calculator and find the permutations formula. Okay, 2 more examples, and I won't go through the calculation here, but I just wanted to explain why you would know this is a combination. Obviously, a big clue is the fact that it says combinations, but there are a few cases where that word is misleading. So for example, we sometimes talk about password combinations, and those are actually arrangements because the order of the letters makes a difference. A locker combination, if you've ever seen those or had the padlock, those are actually permutations as well because most of them require the numbers to be in a certain order. Right, so the common usage of combinations isn't always the same as the mathematical usage. So in addition to that, it's good to just check off the other requirements for combination. Right, so first of all, we have to be picking from the same pool of things. So in this example, we're choosing 3 different flavors of ice cream from 12 flavors. Okay, so it's the same 12 flavors that we just keep going back to and picking. Right, notice that there's no repetition because it says 3 different flavors. So different is often a clue. Right, so that means we're not choosing chocolate, and vanilla. So it's a little bit different than allowing people to pick like 2 scoops of the same flavor. And then the other thing is to check that we don't care about the order. All right, so how many flavor combinations are possible? So in this case, if you mix chocolate, peanut butter, and I don't know, marshmallow, it's still the same flavor combination if you put it in a different order. That's different than the order of the scoops on a cone, but if it's just talking about the flavors, order does not matter. All right, another example is a poker hand. So it's good to know that a hand of cards literally just means the cards that you're holding in your hand, and there's no order that's implied by that. Okay, and if you think about it, if you have a certain number of cards in your hand, you're allowed to play those in different orders. You pick the order. It's not like they're in a set order once they're in your hand. Okay, so the question is how many different 5-card poker hands can be dealt from a standard deck of 52 cards? Okay, and then what is the probability that one particular hand, such as a royal flush of hearts, which is an ace, king, queen, jack, and 10 of hearts. Okay, so what's our clue that there's no repetition? All right. Well, it's actually not the word different in this case, because the different is referring to the poker hand overall, not the cards themselves, which are the things that we're picking. Okay, but the clue here is implied, right? So when you deal cards, you don't deal it out and then put it back in the deck. So that means that you're not repeating, because it's you're always dealing a new card that hasn't been dealt before. And then are we picking from the same pool of things? Well, yes, we are, because we're picking from the same deck of cards. All right, now this is an interesting example because it's the first one that asks us about probability and not just the number of options. Okay, so what's the probability of one particular hand? Well, that would be, actually any particular hand. All right, so for example, the royal flush of hearts. So what we want to know, we want to count the number of hands, not the number of cards in a deck. All right, so that's why it's not out of 52 anymore. All right, and it's not as simple as just counting the number of cards. Okay, so what we want to know is the probability of one 5-card hand out of all of the other possibilities of 5-card hands. Okay, and this is where we use the combination 52C5 would tell us how many ways there are to choose a group of 5 cards from a group of 52 cards. So this represents the total number of hands possible, and then 1 represents the probability of, or the frequency of getting a specific hand. Now, the other thing that's interesting here is that the probability of getting a really good hand is the same as the probability of getting any other 5-card poker hand. It's still 1 out of 52, choose 5, as long as you're still looking at, a specific group of 5 cards. Okay, so let's pause here, and what I'd like to do is just summarize all of the different counting rules that are possible. All right, so we started with the multiplication principle, and that works for when you're picking things from different categories. So, for example, we're picking an entree and a dessert, then you would simply multiply the number of different options in each of those categories together. Okay. Now, there is a connection with combinations now that you know that. All right, so we can do, like if there are 3 appetizers and 4 entrees, you can do 3 times 4, but you can also think of these as combinations. So you'd have 3 appetizers and you want to choose one of them, and 4 entrees, choose one of them, and then multiply. Okay, and just like we saw with probabilities, anytime you have the word and, it means multiply. Okay, so we're choosing 1 out of 3 appetizers and 1 out of 4 entrees, and that's why we're multiplying. Okay, so that's when you would use the multiplication rule. You can also use the multiplication rule when you are choosing from the same category. Right? And you must use the multiplication rule if you're choosing from the same category and looking at arrangements with repetition. So like if I'm choosing letters on a license plate and I'm choosing from the same group of 26 letters, then if I'm allowed to repeat letters, then there is no other shortcut other than multiplying. Okay, you must do like 26 times 26 and so forth. If you're looking at arrangements without repetition, you certainly can multiply, but you can also go on to use a permutation rule. All right, and if you're arranging all of the things that you have, you can do n factorial. All right, so the factorial has built into it this idea of no repetition. Okay, so if you have 10 people and you're arranging all of them in a line, that's 10 factorial. Okay, if you're only arranging some of them, okay, so we can say some or all, then these are permutations. Okay, and then in that case, you would go on to that formula NPR, which has some division to it. All right, it's not the entire n factorial. It doesn't count all the way down to 1. We stop after picking only some out of the things that we have. And then finally, if we're not looking at arrangements at all, we're just choosing. Okay, this is what we call combinations. All right, and combinations built into those as well is no repetition. Okay, then you can use the NCR formula. Now I want to say this in a few different ways, just in case saying it a different way is helpful to you, but sometimes I like to also think of a few different questions as I'm going through here. All right, so the first thing I ask myself is, if I'm trying to count something, is repetition involved? Okay, and if yes, then I know right away to multiply. Okay, if no, then I go on to the next question, which is, does order matter? And if the answer is yes, then I go on to the next question and I ask myself, am I arranging all of the things that I have? And if so, then I use n factorial. And if I'm only arranging some of the things that I have, then I use NPR. Okay, that's a permutation of just some of the things. Okay, if order does not matter, then that's a combination, and I use NCR. Okay, so I hope some of these options are helpful to you. And what I would definitely suggest you do is look through these examples again and come up with a system, whatever you plan to use, to keep track of all of the different counting rules and the types of clues that you would look for to help you know which of these rules to use.